All right, so this AB all transpose equals B transpose A transpose business. I know you're very excited about it, and so I just want to give you three proofs for why it's true. They're all, of course, the same thing, but one of them is more pictorial than the other two. And so we didn't have an example in the previous piece, so here's one. So let's start off with that. 2 by 2. 2 by 2. Don't have to be, of course, but just go through the normal. So this top section here is just the normal business, and then we're going to take the transpose of it. So it's A times B. So you can look at these things. So it's 2, 3. The inner product of those things, minus 2 plus 9 gives us a 7, so on and so on, right? We end up with this result. And all along outside we have a transpose. So that's waiting to happen. So we do the multiplication and then take our transpose, kaboosh. And that for 2 by 2 just means swapping these two off diagonals. These guys stay in the same place. So we end up with a minus 4 here and 11 here. All right. And then this is, of course, in no way a proof. It's just a little example to show that we're kind of on the right track. We figured out that this would have to be the right ordering for a general result because of dimensions of M and N and everything matching up. So good, right? So let's see. So if we took the transpose, I've written the wrong thing, so let me clean that up. This is of course B transpose, A transpose in here. So this is B, goes over to here, take the transpose here, and then this is A over to here, and we'll take the transpose. Good. So the first thing we do is the transpose operation, simple, right? So we get rid of these things. So 4, 3 swaps to here, yep, and the 1, 3 swaps here. Good, so we've done that. And now simply multiply them together, and you get the same result. All right, so that's encouraging, but it's of course not a proof. So here's the, you can often do an enormous amount with simple, by writing things out algebraically. It doesn't, and just sort of machining through. You might not gain as much understanding from it, but you should definitely be able to do this. So let's try that. So we're going to start with A times B transpose, and we'll take the ijth entry of that. So let's think about that. That is going to be so the first step is, well, it's the ijth entry of the transpose. Definition of transpose, right? That is that this is AB, the product of them. It's the jith thing, right? So if this was row 2, column 3 of the transpose, then that's row 3, column 2 of the normal one. So that's an important swap just there, and I'll leave it marked. Well, let's now write out let's imagine these things have certain dimensions. So this one is going to be an M by Q, and this one is going to be a Q by N. Give them that. So let's write out the product rule. So we're going to sum from, I think we can do a K. K equals 1 to Q, right? Where there's inner products of the row of A and so the jth entry, it's the jth row of A, inner product with the ith column of B. So that is A, J, K, B, K, I, right? So this is, all of this is to say, this is the inner product, or dot if you want to say that, of the jth row of A and the ith column of B. Exciting, yeah. Now, this is pretty good. We can now do some switcheroo activity because we're trying to get to the transposes of B and A. So let's just force them in there. So there's some signposting by monks that tell you to do certain things. So let's just say this is A transpose. It's the KJ entry, right? So that, again, these things will swap. We're just forcing, and this is B transpose. We're going to just force the transposes into our equation. We're trying to get from ABs to B transpose, A transpose. Now this looks like a product, but it's not matching up. These things need to match up with each other, so we just swap the order of them. This is pretty great. B transpose, and so now we're going to have IK, A transpose, KJ, and so now this is written in the way that this is the dot product of the ith row of the transpose of B. So the ith row of the transpose of B, it's the inner product with the jth column of the transpose of A, and that is a very nice product rule story. So this is just B transpose, A transpose. It's the I jth entry. So these things are the same. Whoops, I missed it. AB transpose, AB product, transpose, B transpose, A transpose. Good. Now, another way to see that is kind of writing out, it's exactly the same thing, but there's not going to be algebra now. Here we have A and B, just a couple of schematic examples. They have to match on their inner dimensions here, right? So it's M rows, Q columns. We have to have Q rows in B. And let's imagine we're taking the ith row and the jth column here. So this is the inner product of the ith row of A, jth column of B. That's exactly this statement here. And then we can do what we just did on the previous page. We can just flip them, right? This is the jith entry of AB, all transpose. We could start with B transpose first and then A transpose. And we'll take the jth row and the ith column, so we're flipping those two pieces. Now we have N out here instead of M. They look a bit the same, I suppose. I could have chosen some slightly different shapes, but okay. So now this is the, this is the inner product of the jth row of B transpose and the ith column of A transpose. So this is B transpose, Ath transpose, JI. These are the same thing, right? These were the same vectors. I guess that's an important piece to see here, right? So we're using the same vector here, right? So the jth column of B is the jth row of B transpose, and this guy matches here. So those numbers are the same. So that dot product has to be the same, right? This inner product of these two, of this row with this column, is the same as this one with this one, because they are the same beasts. And so we just sort of figure out what they are, and we get that one of them is the JI entry of B transpose, A transpose, and the other is the JI entry of AB, all transpose. So that's very similar to what we just did. Okay, one last piece. Definitely giving you a good serving here. This is for the very excited. So this is yet another way, and then we'll be good. Right, so A times X transpose M by N in here, and this is M by 1. Let's just think about this. We'll get back out to B, to A times B. Okay, so if we do this, this is really, well, let me write it like this, column picture, right? A2 plus, plus, yes, excitement, the excitement builds. This is column picture. We just use all these things as much as we can. Column picture. Not to be confused with the Colin Firth picture. Okay, who will be dismayed by all of this. So this is x1, A1 transpose plus da 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 plus xn an transpose. So this is a sum of row vectors, right? This is a row vector. And we could write this as x1. This is the sneaky thing where we say, well, we could write it like this. We could stack those row vectors, A1 transpose, A2 transpose. We could stack them like this, AN transpose. This is the same thing. So what is this though? This is actually x, the vector x transpose times A transpose. You know, this is a result we knew, of course, but we're extruding through, right? So this is just, well, what am I saying? Right, it's not enough. We've just done matrix times a vector. So now we need to get out to our main goal, which is A times B transpose. So let's write that, sort of inspired by this result. So this is next. Yep, that's good. And then we'll write all of these as a bunch of column vectors. We use some advanced matrix wrangling, which is a thing, right? So this could be, this would be n. Yeah, this is, again, m by q and q by n. So it has n column vectors, this B thing. So we'll write that out. There's a great big set of brackets around it with a transpose. And we know we can just multiply in and the A will hit each column. Right, so there'll be A times B1, A times B2, A times Bn. Very, very nice transpose. And this is all in a nice big matrix. That was one of our results if we're multiplying from the left. This resultant matrix only has columns of A combined to give you the new columns, the rows of B combined to give you the new rows. That was an advanced thing. We can now, right, so we have a good thing. We can take the transpose, so act the transpose through here. So this column becomes a row. So we're going to end up with A, B1 transpose across the top, A, B2 transpose. See, easy, right? A, B. You have to bite sticks a lot, lots of sticks. It's good to have a good pain stick around. That's right. And then we know something about this result. That's why we did this one before. Right, so we know what, if we take the transpose of A times vector, then that flips. So let's use here. I should get rid of this bit. Yeah. Not all of it. Use here. Okay, great. All of these things will now be B1 transpose A transpose, boom, boom. B2 transpose A transpose. Right. We have the little flip in here, and the last one is Bn transpose A transpose. And so all of them are being post multiplied by A transpose, all of these row vectors now. So we can pull the A out. One more piece. So we've got B1 transpose, down to Bn transpose. I know it hurts. And then what is this? This is B1, so it's the first column of B1, then the second column, then the third column, right? Laid across each other. So that is really B transpose A transpose. Yes. Yes, it's true. All right, so that's a little bit of a victory for us. You can look through these. You may like these proofs in different ways, but certainly don't forget the result. Very, very useful things. Transposes and symmetric matrices are completely awesome. All right.